Welcome back to our engineering mechanics lectures, in which we're picking up where we left off last time, and that is moments. But we today take it a step further and we will talk about moments in 3D. In fact, our real goal here to begin with is to expand our in-plane force knowledge and turn it into an understanding in 3 dimensions. And to do that, I need to really introduce how we're going to use the vector product so that you know the mathematical rules that apply in the 3-dimensional force systems. And then, of course, as always, our ultimate goal is to actually calculate some of these systems and to determine the moments that are acting in these 3-dimensional systems that I will introduce to you today. So let's get started and talk about the vector product, which most of you probably know as the cross product. But starting from today, I really encourage you to think of it as a vector product, because that will always remind you, in opposite to the scalar product, that the final result must be a vector. And that is very important to understand, because often I see students answering these types of questions with a single number, and a single number, as you know, is a scalar and not a vector. And these moments in 3D really require a vector response. So we need 3 directed rotations, if you will. And I will explain, of course, that to you today. So let's get started and let's pick up where we left off. And so I want to recap real quick that we used to have a 2-dimensional coordinate system, and we usually have a 2-dimensional coordinate system that looks like that: x in the horizontal, y in the vertical. And now I want to introduce a third direction, which we already talked about last class, that would mean if you have anything acting in the 2-dimensional xy system. So for example, let's pretend I have, I don't know, a balcony here. So let's say this is a balcony that is attached to a wall right at the origin. Then you would calculate the moment, let's say, at the origin, and what you calculate is really a rotation, or the potential for a rotation, about the z-axis. Please remember that from our last lecture. So let's say I have a force acting on the system that we all know at this point how that works. Force times lever arm, right? So we have F1 here, and then the lever arm, of course, would be down here. So let's call that L. And really what you calculate when you take the force times the lever arm is the tendency of this lever arm to rotate about the z-axis. And that is a nice thing to know when you deal with 2D systems like this lever arm here. But often you don't have the luxury of really dealing with a planar system, and we need tools to understand how 3D systems work. So let's just draw a 3D system. And for that, I'm using my regular x, y, z coordinate system, in which the x-axis is actually coming out of the plane. It's not different from what we had before, but this is just how we do it in this class, just so that the z-axis is actually acting upwards. And now I place a random structure in there. Let's say it's a pipe structure. Doesn't really matter what it is, but let's make our life easy and have a structure that is acting here. And to symbolize where it's acting in 3D, I'm using my dashed lines as always. And so I parallel move my x-axis and of course my y-axis. And so now we have description of the lever arm in a 3-dimensional space. And let's now say that I have a force acting on there in some random space. So let's say that would be acting right there. So this is my F. And now it's very difficult to do the force times the lever arm. And don't get me wrong, you can of course calculate the lever arm from here to here, and let's call that L. And you can, of course, calculate F times L, but what you will find is a moment that rotates about the origin that may be of interest to you, but you may not know in which direction it's really acting. So it would be much more interesting for us to actually find moments that are acting along the axis. So let's say I have a moment in this direction and a moment in this direction and a moment in that direction. So what I'm really after is these double arrows, so that you understand that I have, for example, here I would have a moment about the x-axis, here I have a moment about the y-axis, and here I have a moment about the z-axis. And then, of course, there's a resultant of that, and the resultant would be equal to F times L in this case. But let's just understand for now that we need a tool that can help us to calculate these three entities so that we understand what we can do if we don't deal with a planar system, so that when it's somewhat random in space. And of course, the headline already gives it away. We obviously have to deal with the vector product, and you can already tell what the vector product is, right? It's a vector that gives us three results in 3D space, and therefore the answers will actually be mx, my, and mz. And so let's talk about that first conceptually, and then let's apply it. All right, so first let's just draw a random lever arm and a random force. So I have two entities here that are random to each other, and let's say this is my force here. So this is F, and then this I call R, and those are both vectors in this case now. And let's pretend that R has an origin here, and so we're trying to find the moment about this point at the origin. So we're trying to find this moment, right? And to properly describe this, of course, we need to know that we have an angle here. Let's call that angle theta. And we kind of talked about this already, but let's reinforce this, that our formula is usually m about the origin, so MO, so we call this here the origin, in any space direction now, is really nothing else than R cross F. And of course, these are vectors, and therefore the moment actually becomes a double vector, right? Because it rotates about a certain point. And you may remember this formula from your mathematics class, that this is also equal to R magnitude times F magnitude times the sine of theta, right? And why does this work? That's the big question, because remember that for a moment you always need F times D perpendicular lever arm, right? So I want to talk about the perpendicularness again. I know we did this already in our last lecture, but please understand that I use the sine theta to really turn R into something perpendicular to F, or I turn F into something perpendicular to R. So for example, if I wanted to look at the system as such that I have a perpendicular lever arm right here, so in this case, it would be the hypotenuse would be R, and then I have the adjacent here to the given angle, and I have the opposite given here. And this opposite is perpendicular to the force, and so this distance is really nothing else than R times sine theta, right? This comes from your basic geometry, or trigonometry, I should say. So you can use this formula because it turns the lever arm, in this case, into something perpendicular to the force. And this works in 3D space as well, right? It's obviously difficult to show that. It's easier to think of it in a, like, what's seemingly 2D here, but in reality, it works in any scenario. And I will give you a formula for how to calculate that in just a second. Before we do that though, please let's understand one very important basic concept that we probably already remember from high school. And that is when we have two vectors. Let's say I have vector A here and I have vector B. Let's say, in this case, make our life easy. It's right here. And I take A cross B. So let's say I want to have A cross B. And B is the purple component. So what do I do if I have A cross B? If I have A cross B, let me use a different color here. I'm going to underline this. If I do A cross B, I rotate from A to B. And what I will get actually is, think about this please, like the rotational sensor we talked about before. If I rotate my bottle cap from A to B, I'm really turning down into the plane, if you will, right? So, or downwards in this case. So let's say I have a rotational axis, it would really go down in this direction. So this would be A cross B. And please note a very important aspect, that this is mutually perpendicular to both of these vectors. So the rotational axis must be mutually perpendicular to the plane that is spanned by A and B. And that would go in line with our red line here. Let me box that properly or double underline that properly. So that would be this component. But I can also move in another direction. I can also cross B with A, right? And what would I find if I were to cross B with A in this case? So let's look at that and think of this as the orange component, the orange rotational sense. So of course I end up with a vector as well, but it's in the opposite direction, has the same magnitude, but this would be B cross A. And so therefore I should indicate this properly and understand the most important thing about all this is that A cross B is not equal to B cross A. That's why I gave you this drawing here, and that's why we went through this whole exercise. A cross B in magnitude is the same as B cross A, but it's directed in the opposite direction. And it really comes from the right-hand rule or the bottle cap rule, right? So think of this as rotating from A to B or from B to A, and you end up with something different. And that's why I also always used already this definition when I said, hey, let's rotate the system from positive x to positive y. Remember that we said that's how we measure angles all the time and so on? And that is because of this rule here, because of the right-hand rule, that the cross product really works. So if you rotate from positive x to positive y, you get a positive moment in the z direction. If you rotate from positive y to positive z, you get a moment in the positive x direction, and so on and so forth. And that is why it's so important that we use the right-hand rule properly, right? So please understand that A cross B is not equal to B cross A, and it can make a huge, huge difference. Now, let's move on and think about that formula or the concept of that moment with one more thing. And for that, I use my vectors again. I think I called this here B. And I had a second vector, which is A. And what is A cross B really doing? Remember, so A cross B is nothing else than A magnitude, B magnitude times the sine of theta. Now I want to give you one more physical interpretation of this. What is A sine theta? A sine theta is really giving you this component, right? So this is A sine theta. And that is why you can also use this formula to really calculate the area in a trapezoid, right? So if I give you a trapezoid here that is represented by A and B, So if I move that here, then remember that in a trapezoid, what do you have? You have the area. So the area of a trapezoid is really nothing else than base times height, right? And the formula is usually referring to this as the height. And so the base here is really nothing else than b, which is the base, times the height, which is a sine theta. And so this component here is really nothing else than the height. And so that is why sometimes the cross product is actually used by computer programs to calculate the area, because you can break any area usually down into many small finite trapezoids, and you can describe the trapezoid by A and B, and then you can use that to calculate the area of the entire system that is made up of many small trapezoids. So this is a very important concept to understand for engineers when they try to approximate an area. So I highly recommend that you understand this by heart, and you need to use that formula anyways. But I believe that this covers all the formulas that we need in a general sense, and that we now understand that A cross B is not equal to B cross A. But the last thing we need is, what do we do if we have the force given to us in a three-dimensional description and the distance also given in a three-dimensional description? How do we numerically interact with that? For now, please understand that we are really calculating the force times the lever arm, but we're kind of doing it component-wise to really arrive at these three different components, which so far we don't get. Here you only get the magnitude. That's where we left off in our last lecture. But now on our next page, I want to show you what to do if we have ijk components for F and ijk components for R, or what I termed L here in this picture. So let's move on to the next page and think about how to deal with that.